Hello, welcome back. We're embarking on an entirely new topic from what we have learned recently. We're embarking on the topic here in the beginning of sequences in math, and then we will be transitioning into the related topic of series. So what we're going to do in the beginning is make sure you understand what a sequence is. To solve problems involving sequences, we'll transition into series. We'll talk about the sigma notation with the big capital E, Greek letter E that you see in math, and learn about the applications of those ideas. Now, in the biggest picture, people want to know in the very beginning is, why do I care about sequences and series in math? It's really hard for me to tell you exactly why, because it involves future math, things that you haven't learned yet. But I'll tell you in a nutshell, the foundations of calculus, which all modern science, engineering, and math calculations are done using the concepts that we learn later in calculus. The foundations of calculus really are built on the concepts of sequences and series. Because later on in calculus, we will learn how to look at a curve and figure out how fast that curve is changing. In order to do that, we'll have to zoom in on that curve and look at what's happening at a small region. We will also take a function, a curve, and we'll be calculating the area underneath the curve to kind of add up what is really going on to be able to calculate things like trajectories in physics and other related concepts. So the applications of calculus are really limitless. In order to do the main ideas of calculus, we have to understand what a sequence is, and we have to understand what a series is, because those concepts in calculus are built upon these. The good news is sequences and series are very simple to understand. A sequence, which is the topic in this lesson, we're going to talk about introduction to sequences, and specifically we'll be talking about the introduction to the arithmetic and the geometric sequence. All right? A sequence is just a listing of numbers. That is it. Right? If there is no pattern to the listing of numbers, then the sequence has no pattern. But there are some patterns that exist and pop up in nature called the arithmetic sequence and the geometric sequence. We're going to study those in detail in future lessons. This is just an introduction to the general concept. So in general, a sequence, which is where this entire journey begins, is just a list of numbers. In your math book, you'll see a much longer definition, but ultimately when you boil it down, it's just a list of numbers. So when would we care about sequences? What is a practical example of a sequence? Let's talk about the temperature in this room, every day at 5 p.m. I come in every day at 5 o'clock in the afternoon or in the evening, and I measure the temperature and I write it down. The next day I do the same thing again and again. So if I'm going to take a look at a practical example, I might look at the temperature at 5 p.m. in this room. And the temperature might go something like this. On day 1, it's 15 degrees Celsius, and then 17 Celsius, and then 14 Celsius, and then 13 Celsius. Let's do 15 Celsius, like this, right? And so I might list these numbers on day 1, day 2, day 3, day 4, day 5, and then I might say, dot, and then I might have some final temperature T sub n, okay? So I guess I should have put this probably on the same line. You have a list of numbers, maybe you get more and more numbers, and then you have T sub n. The T sub n is the temperature at some day in the future. Usually in sequences, we use the letter n to tell us on whatever day we're doing the measurement in this case. Or if I'm taking some measurement every second, it's basically n tells you what number the measurement is that you have. N just means it's the index that tells us what number of measurement we have. So this would be day number 1, 2, 3, 4, 5, 6, and so on and so forth. And so this first guy all of these guys are what we call terms of the sequence, right? So all of these things are what we call terms of the sequence. You're going to see me write SEQ for sequence quite a bit. All right? So for this first guy, this first one right here, this is T sub 1. It's the very first term in the sequence, right? And you might guess that the one next door is T sub 2. And this one is T sub 3. And this one is T sub 4. You can see the progression. Dot, and then I'm going to have some temperature measurement so many days down the road, T sub n. So what it means is the sequence might have only 3 terms, in which case it has just these first 3 numbers. These guys don't exist, right? If I go out to 5 days, then I might have 5 days in my sequence. Okay? And if I go at 7 days, I'll have some more terms in the sequence. And so I generalize it and I say the nth term is just the last term at the very end of the sequence. That's all it means, t sub n, right? Now, if you look at this thing and try to figure out what pattern you have, you'll realize quickly that there is no pattern to these numbers. So I'm going to put that right here. There's no pattern. There's no pattern here. So 15 plus 2 is 17, okay? But then 17, you're going down to 14, and you're going down by 17 minus 3 is 14, so you're going down by a different amount. Then you go down by 1, then you go up by 2. So the numbers are jittering around all over the place, and that is because the temperature in a room is, I don't want to say it's random, it depends on the weather or in the air conditioner, but it's not something that's going to follow a logical progressive pattern like this. Okay, so we would say that there's no pattern in this sequence. Sequences like this are very important in the real world. There's lots of processes like noise, like the jittering of the stock market that aren't really, you can't really predict what's going to happen in the future. But there are a lot of patterns that do follow a regular pattern. Okay, let's take a look at another type of sequence just to get an idea. Let's take a look at the value of some investment that I have. What I mean by that is I might invest some money into a stock. Let's say I'm going to buy some Google, right? And I'm going to put $100 into Google. Well, that price of that stock is going to go up and down each day, and it's kind of not predictable what's going to happen. It depends on the stock market, depends on the economy, it depends on the amount of fear and greed in the stock market on that particular day. So it's going to kind of go bouncing up and down a little bit. So if you were to look at the sequence that is because of some value of an investment, on day 1 you might have, it might be worth $100, but on day 2 it might be 102. You're happy, you gain some money. And you're really happy, it might go to 106. Then it starts going down to 105, 101. And then you might have some days down the road, call it t sub n. You need to get used to seeing this t sub n being out there. So these are the terms of the sequence, and you label them just like we did the ones before. So this will be term number 1, term number 2, term number 3, term number 4, term number 5, and you might have more measurements, but eventually you're going to get to some term n, some however many measurements out in the future. And again, there's no pattern to this one, so I'll put no pattern. To figure out a pattern, you're looking at the numbers and you're just trying to figure out some rule to allow you to predict ahead of time what the numbers are going to be. But these are random all over the place. I mean, yeah, they're all around $100, but they're some up, some down, and you can't predict ahead of time what it's going to do. If you could predict the stock market, you would be rich. Nobody can do that. So let's talk about something that actually does have a pattern. And so that's going to be our first, what we're going to end up calling arithmetic sequence. All right? So let's talk about some bank account. Not an investment, just some bank account. Bank balance. Let's look at some bank balance. All right, first you take a look at it and you have $3. Then you have 6. Then you have 9. Then you have 12. Then you have 15. ... And then someday in the future, you have some amount of dollars in the bank there. Obviously, you would, for it to be a sequence that is some kind of pattern, you would need to be able to predict ahead of time what the future balance would be. Now, this one looks quite a bit different because you can see what's happening is I'm depositing $3 every day into the bank. So this is day 1, day 2, day 3, day 4. And so if I wanted to label it, I would say, this is T sub 1, this is term number 2, term number 3, term number 4, term number 5, and then term n. And I just kind of spilled the beans, but what's happening here is every day I'm adding an additional $3 in. This is a predictable pattern. I know what the pattern is, and because of that, I can go predict, this thing goes up to T sub 5, the 5th measurement on my bank account, but knowing the pattern, I can predict T sub 15 if I want to. I can go predict T sub 25 if I want to. I can predict T sub 100 if I want to. I can predict as far out in the future as I want because I know what the pattern is. And just to spell it out, what's happening here is you look at adjacent terms. When we talk about adjacent terms, we just mean the terms that are right next to each other, right? So if you look at this term and this term, what you figure out between this term and this term, the difference between here, I'm going to call it D. The difference D is how many dollars? 6 minus 3, that's $3. I'm going to drop the dollar signs from here on out to make it easy. What is the difference between this term and this term? 9 minus 6. Again, that's the difference being $3. What is the difference between this? You see the same thing. The difference is $3. The difference is $3 because every time I'm subtracting, I'm getting exactly the same difference. That is what constitutes the pattern. This one was very simple because it's just small numbers, but ultimately what you want to look for is look at all the adjacent terms and see if there is a what we call common difference. The difference is $3 and it's common to all of the terms. So the sequence is governed and defined by that common difference. So this kind of sequence that basically is governed by a common difference between terms, that is one of the most important sequences you'll ever learn about in math. It's called the arithmetic sequence. You can think of arithmetic meaning like arithmetic. Arithmetic is usually addition and subtraction. That's what you think of when you think of arithmetic, right? So the way you remember it is arithmetic sequences are just sequences where I'm adding a constant number to each term and subsequent terms. So that's what an arithmetic sequence is. So we need to kind of write this down and make sure that we are all together. All right? So what we know is that this is called an arithmetic sequence. Okay? And this is when terms, adjacent terms, when I say terms, I mean the terms right next to each other, they only differ by a common difference. I'm going to underline this because it's the most important concept. The common difference, that's the term, that's the idea you're going to see in your book. So the common difference in this case is D is equal to 3 in this case, in this example. So the definition of an arithmetic sequence in your book that you'll probably see is something like this. It'll have a lot more words and a bunch of stuff that doesn't really matter. But ultimately, all it means is a listing of numbers where the difference between the numbers that are next to each other, is always the same thing. So the difference here was 3, the difference here was 3, the difference here was 3, and the difference here was 3, so it's arithmetic. If the difference was 3, 3, 3, and then right here the difference was 4, then this would not be an arithmetic sequence anymore. Because in order to be arithmetic, every number in the sequence has to differ by a constant number. So if this differs by 3, then this differs by 1, and this differs by 3, then it's not arithmetic anymore. So it's very simple. All you have to do is check every pair of numbers and see if they all differ by a constant difference. And you need to write that constant difference down, or that common difference down. We call it D. All right? And of course, the example here being the bank account balance of depositing $3 every day, that's a relatively easy to understand idea behind arithmetic sequences. So that was the arithmetic sequence. Now we need to kind of touch on and introduce the cousin to the arithmetic sequence, and that's called a geometric sequence. So if we think about it, when you have an arithmetic sequence, it means arithmetic, right? All you're doing is adding a common number you're adding a constant common difference. You're adding a number to each subsequent term. That's all you're doing. Also, D here can be negative. So here we're adding 3, but it would be perfectly fine if D were equal to -3, -3, -3, -3. That would mean the numbers were going down in the bank account balance. So it might be, 100, and then 97, and then you subtract 3, and subtract 3, and subtract 3. That's still arithmetic. Whether the numbers are going up or the numbers are coming down, the common difference can be positive or negative. That's totally fine. It's still arithmetic. Now, what do you think another kind of sequence might be worth studying? A sequence that doesn't involve addition or subtraction of adjacent terms. It might make sense that we might study terms and sequences that don't differ by addition and subtraction, but that differ by multiplication. And that is an incredibly important sequence also. It's called the geometric sequence. All right? So let me write it down and give you a practical example. That was arithmetic sequence right here. Now we have the geometric sequence. Underline this. And this means that adjacent terms means terms that are right next to each other. I'm going to reword it a little bit, but ultimately what it does mean is that those adjacent terms have a common multiplier that goes between the terms. So instead of a common difference, it's a common multiplier. Keep that in the back of your mind. I'm going to write it down more like your book will talk about it, and then we'll give you an example. It'll be crystal clear. Adjacent terms have a common, you might think I'm going to write down common multiplier, but I'm going to write it down as common ratio. This is what you're going to see in your books. I'm going to teach you the way all the books talk about it, but I'm going to show you how easy it is to understand. And the common ratio is not called D, it's called R, because R for ratio, right? So that means pairs of terms have a common multiplier. All right, this is what the definition of a geometric sequence is. Now let's practically talk about it because it's actually much easier to understand than this thing would leave you believe. What if I give you a sequence that looks like this? 2, 6, 18, 54. This is the sequence. And it's a good idea in your mind, at least, to say that this is term 1, term 2, term 3, and term 4, just like I've listed them here. But I'm not going to write down the terms underneath. You just need to know that that first term is term 1, the next one is 2, then 3, then 4, and so on. So is this an arithmetic sequence, yes or no? All you have to do is say, am I adding a constant number each time? Well, the difference between here and here is 4. And the difference between here and here is definitely not 4. And the difference between here and here is definitely not 4. So it's definitely not an arithmetic sequence. The next thing you have to ask yourself is there a common multiplier between terms? Well, if I look at this, 2 times 3 is 6. So I'm going to multiply by 3. And then 6 times 3 is also 18. So this is also multiplied by 3. And then if you get your calculator out, 18 times 3 is also 54. So for the terms in the sequence, for everything that we have written down, this is what we call a geometric sequence because the terms have a common multiplier. It allows me to predict the terms in the future. Remember I said, in order for the sequence to have any usefulness, I have to be able to predict down the road. And knowing this rule, I can predict again, term number 4, term number 5, term number 10 if I want to. I'll just keep multiplying by 3 to get all the terms in the sequence and I can write them all down. All right, so if this common multiplier thing is here, then why does this definition talk about a common ratio? Because when you think about what does the word ratio mean, ratio is the division of things. So when two terms have a common ratio, it's exactly the same thing as saying that they have a common multiplier. This common multiplier wording is my wording. It's not wording that you'll see in a book. Most of the time you'll just see that the geometric sequence has a common ratio. So here's what I mean by that. Notice I said times 3, times 3, times 3. But let's look and see what the ratio of 6 to 2 is, because that's what a ratio is. What is 6 divided by 2? Take this divided by this. Well, what do you get? You get 3. Let's look at this common ratio. 18 divided by 6. What do you get? You get 3. Let's look at this common ratio. 54 divided by 18. What do you get? You get 3. So you see, the common ratio between these two terms is 3. The ratio between these two terms is 3. The ratio between these two terms is 3. The common ratio, R in this case, is equal to 3. That is what you're going to need to write down when you're defining the geometric sequence. You want to figure out what the common ratio is. It's exactly the same thing as saying what is the common multiplier. But they don't usually phrase it that way in books. They want you to tell them what the common ratio is. That's okay. That's all you're doing when you look at this anyway. We know that 2 times 3 is 6. The reason we knew it is because we memorized it. But really what you're doing is you're taking 6 divided by 2 and you're getting 3. You're taking 18 divided by 6, you're getting 3. You're taking this divided by this, you're getting 3. So whether you think of it as a common multiplier or a common division, common ratio between them, it's the same exact thing. What you want to know in this case, that the common ratio R is 3. And for an arithmetic sequence, it's not multiplication or division at all. It's only if the terms differ by some common difference, which can be positive or negative because addition and subtraction are basically the same thing, ultimately. All right? That's all you really have to worry about. People stress out so much about what an arithmetic sequence is versus what a geometric sequence is. That is the difference. So let's solve a couple of quick problems to really get a handle on this. What I want to do is I'm going to write down this sequence and I want us to figure out together, is it an arithmetic sequence, is it a geometric sequence, and also to predict the final two terms of the sequence. Pretty simple stuff, nothing above basic addition or multiplication. So what if you have 20, 17, 14, 11, and then some number right here? I want to predict what these are, but before I do that, I want you to tell me, is this arithmetic or geometric? And then how do we predict what these are? So you have to say, well, is it arithmetic? What I need to do is look at the commonality in the terms. I'm going to look at this and say, what is term number 2 minus term number 1? 17 minus 20 comes out to -3. D is -3. The difference. What is the difference here? 14 minus 17. The D is again -3. What is the difference here? 11 minus 14. D is -3. Remember I told you D can be negative. All that means is the terms are just subtracted going down like this. So the common difference, D, in this case, is -3. So because of that, we know this is arithmetic sequence. That's all you need to know. Right? Now, in order to predict, this is term 1, 2, 3, 4, in order to predict term number 5 and term number 6, I need to use this definition. Right? So how do I do that? Well, what you say is term number 5 is going to be term number 4 plus the common difference. But the common difference is negative. So it's going to be 11 minus 3. You're adding the common difference, but the common difference is negative, so you're really subtracting it. So what you figured out is term number 5 is, what do you get there? 8. Okay? And then, in order to figure out what term number 6 is, I need to know what term number 5 is. So it's 8, but then I have to add that common difference. The common difference is negative, so it's really a subtraction. Term number 6 is 5. So that's what you get right there, 8 and 5. So if I wanted to write the sequence down, I would write 20, then 17, then 14, then 11, then 8, then 5. And you would see every one of these have the same common difference. In fact, if you look at these two that we just calculated, the common difference, 5 minus 8, again, is -3. It's the same common difference. That's all you have to do when figuring out if something is an arithmetic sequence. Now let's take a look at one more, and it probably won't be a big surprise, and it's going to end up becoming a geometric sequence. Let's say 1, 5, 25, 125, and then something and something else. I want to figure out what these two are, and I want you to tell me arithmetic or geometric. Well, if I look at the common difference, 5 minus 1 is 4. The common difference here, 25 minus 5, is 20. So the common difference is automatically not the same. But I can realize that if I want to look at the common ratio, 5 divided by 1, that's 5, right? And then what's this? 25 divided by the next door neighbor, 5. That's also equal to 5. And then I can go here, 125 divided by 25 by its neighbor. That's 5. So the common ratio, which means the ratio between adjacent terms, is the same thing. It's 5. That means to go from here to here, it's the same as multiplying by 5. To go from here to here, the same thing is multiplying by, not by 3, sorry about that, by 5. And then to go from here to here is multiplying by 5. It's a common multiplier, same thing as a common ratio. So to write down our answer, we figured out the common ratio, we call that R, is 5. And because it has a common ratio, we know it's a geometric sequence. So we circle that. That's the first thing we want to do. Now we want to predict. This is term 1, term 2, term 3, term 4. We want to know what term 5 and 6 are. So what is term 5? What is it going to be? It's going to be 125 multiplied by 5 again. 125, and I cannot write today. 125 multiplied by 5. So term number 5 is, when you multiply that, you get 625. Just double checking myself. And then term number 6 is dependent on its next door neighbor, which is term number 5. 625, again, common multiplier of 5. And what you're going to get is 3125. So this is term number 6, this is term number 5. So if I wanted to write the whole thing down, it'd be 1, 5, 25, 125, 625, 3125. And again, the common ratio holds. If you grab a calculator and divide 3,125 divided by 625, what are you going to get? You're going to get that common ratio of 5, because all the adjacent terms differ by that common ratio. So in this lesson, we have introduced the concept of sequences. Before starting this lesson, you may or may not have known what a sequence is at all. We've now talked about the idea there's lots of sequences. Most of them don't have any real mathematical value because they're kind of random. Temperature in a room, value of some investment being unpredictable like that. Those are also sequences, but they aren't labeled with the term arithmetic or geometric, and we can't predict ahead of time what they're going to be. An arithmetic sequence is like an example of a bank account where I'm adding money in every day. The common difference between terms is just a number. That is what defines to be an arithmetic sequence. A geometric sequence is when you look at the next door neighbor terms and they differ by a multiplier. 2 times 3 being 6, 6 times 3 is 18. We talked about why the division of adjacent terms is called the common ratio there. Now we have a lot more to do with this. We're just scratching the surface. The next couple of lessons, we'll do some more problems to give you more practice with the introduction to sequences. And then we'll be diving in a lot more detail into arithmetic and geometric sequences in the coming lessons. So make sure you understand this, then follow me on to the next lesson, and let's continue cranking through sequences in series.